Hi, and welcome to a special topic video in fluid mechanics. We're going to explore the role that fluids play in the design and locomotion of robots. These types of robots span from small, micro-robots that deliver medicine inside your body to large, uncrewed air and water vehicles. In all these cases, fluid mechanics plays a major role in the robot function. Today, we'll start with a very basic overview of the forces a fluid produces by exploring the Navier-Stokes equations, which is just a fancy form of F equals ma. Next, we cover different flow regimes and how the size and speed of your robot may change how the fluid reacts to its motion. Lastly, we will go over rectilinear motion, meaning moving in a straight line, and how to estimate the drag you will encounter and the different ways to produce thrust. Let's jump in. Almost all travel is through some sort of fluid on the planet, meaning a liquid or a gas. So, entire fields of study are dedicated to how we best move through these fluids. Consider our planet. We are surrounded by water in lakes, rivers, and oceans, and air in our atmosphere. Your first question might be, is there really a difference between liquid and gas? Don't they both obey fluid mechanics principles? And yes, you'd be right, but there are major differences between the two classes of fluids that need consideration when designing a robot to move through them. Let's briefly consider how liquids and gases are different. First, liquids are very heavy, meaning they have high density, whereas gases are relatively light. This is important because fluid forces tend to scale with density, so water forces can be much higher than air. Second, liquids are incompressible. The density can be assumed constant. In a gas, if you move fast enough or you push it hard enough, you can compress it, dramatically changing the equations you use to calculate force. Liquids have relatively high thermal mass, so cooling a robot in a liquid might not be an issue, whereas gases are poor heat conductors and cooling needs special attention. Liquids have the option of being non-Newtonian, meaning the viscosity is a specific function of the flow shear or velocity gradient. This is important in many microrobotics areas where the working fluid is blood, because blood can be non-Newtonian. Gases are almost always Newtonian. Lastly, in water, buoyancy is your friend. It helps you keep and control your vertical position. In gases, you generally need lift to keep you in the air. This is why fish and birds have evolved to look so different, despite both using fluid for locomotion. So we accept the fact that we need to move through a fluid, and in many cases the fluid itself is important. How specifically does a fluid make force? There are dedicated areas of study to this very question. Specifically, fluid mechanics is the study of fluid motion and forces due to that motion. Aerodynamics is a subset of this, focusing on vehicles moving through the air, and hydrodynamics focuses on vehicles moving through the water. Regardless of the fluid, they obey one main law, Newton's second law, or F equals ma. A change in the momentum of a particle must be due to force. In fluid mechanics, it's a bit more complicated than F equals ma. Our version of F equals ma are the world-famous Navier-Stokes equations. Here, I'm writing out the incompressible version of the Navier-Stokes equation, meaning density is assumed constant. There are three of them, one for each direction, where the white x's and u's change to y's and v's, or z's and w's for the other two directions. On the left-hand side, we have the ma of F equals ma, where there is the time acceleration and the convective acceleration. On the right-hand side, we have the pressure term, viscosity terms, and a term associated with the generic body acceleration. Now, you don't need to be able to solve these equations for robotics. They're actually famously impossible to solve. But what we do need to know are where the forces come from. The left-hand side are all terms dedicated to fluid acceleration, or how the fluid responds to the force by accelerating in time or space. On the right, we have the three force sources. First, pressure forces. A pressure gradient acting normal to the surface of a particle makes a force, and that force induces motion. Second, we have viscous forces. If the flow above you is moving a bit faster or slower than the flow below you, you feel a net force. These are primarily tangential, much like friction of sliding on solid surfaces. Lastly, we have the body force. This is generic and can be any special type of force that somehow moves a particle without touching it. Big examples here are gravity, magnetism, Coriolis, etc. When you move through a fluid, you cause the fluid to accelerate and thus you feel these forces, which is why it is important to understand their nature. In order to solve the complicated equations, we often make assumptions like neglecting some force sources. So we often find ourselves asking which force matters most, and that is problem dependent. Pressure forces are most dominant in large vehicles that are moving relatively fast. For example, an uncrewed underwater vehicle. Viscous forces are dominant in smaller, slower vehicles like micro-robots in your bloodstream. And lastly, body forces are really only for special occasions, like if you've designed a robot that specifically interacts with a magnetic field. To categorize our flows and define flow regimes, fluids people really love to use non-dimensional numbers. Non-dimensional numbers let us compare quantities relative to one another. One of the most popular non-dimensional numbers is the Reynolds number, which is a dimensionless ratio that compares the viscous forces and the inertial forces of the fluid. I should note that we can't dive too deeply here, but full derivations of the Navier-Stokes equations and non-dimensional numbers like the Reynolds number can be found in other videos on my channel. Generally, the Reynolds number is the inertia force divided by the viscous force, which is density times velocity squared times length squared divided by the viscosity times the velocity times the length. This simplifies to be rho UL over mu. These velocities and lengths are references or scales, meaning they depend on your problem. For a robot moving in a fluid, this would be something like the average velocity of your vehicle and the vehicle length. The Reynolds number is large when you're moving fast, you have a large vehicle, or if the fluid is heavy. It is small when you're moving slowly, you have a small vehicle, or the fluid is very viscous. Using the Reynolds number, we know what fluid force sources we can neglect when considering our flow. For example, when the Reynolds number is very large, we can ignore the viscous forces, meaning viscosity goes to 0. When the Reynolds number is very small, we can ignore the inertial forces, which is like neglecting the density. We use the Reynolds number to tell us which equations we need to use to find the forces on our vehicle, because these assumptions change the equations. Now that we've had a crash course in fluid mechanics, let's pivot a bit and consider our robot motion. Say we have a robot moving through a fluid. Our fluid has properties of density and viscosity and could be a liquid or a gas. We're only moving in one direction, which causes a flow to pass over a robot with velocity u. The flow induces a drag force on the robot, which we represent with d. And, in order to move, the robot needs to produce some type of thrust force, which we call t. For steady, rectilinear motion, where the velocity is not changing in time and you're moving in a straight line, we need our thrust force to balance our drag force. The thrust force is determined by the robot, and the drag force is determined by the fluid. Although in reality these are tied together, because the drag force is a function of the velocity, which is a function of the thrust. Let's dive into the drag force and thrust force separately. Drag force is the force on a vehicle due to the fact that you're trying to push a fluid out of the way as you move through it, and it's resisting your pushing it. Consider an object in a flow field where the flow has velocity u and the fluid has density ρ and viscosity mu. There are two main ways this object can feel drag. First, we have drag due to pressure difference in the front and back of the cube. If there is a pressure difference, we know from our Navier-Stokes equations that we have a force, and that force is something called the form drag. Alternatively, on the sides of our cube there is a boundary layer due to viscosity. This is because at our surface the velocity of the fluid must match that of the object, and far from the surface the velocity must match the free stream, so we get a gradient of velocity. The gradient induces a flow shear, which makes a shear stress, which makes a force on the side of our cube opposite the direction of motion. This force is called the skin friction drag. Skin friction and form are the two types of drag a vehicle can feel. Now, I want to be able to get us to the drag equations without needing to go through a bunch of complicated fluid mechanics. Luckily, we can do just that without knowing any physics at all through something called dimensional analysis. I'll go fast here, but I do have an entire video dedicated to dimensional homogeneity, which is the strategy we're about to use. To put it simply, we're just going to make sure that the units on one side of the equation match the units on the other. No other physical principles are needed. You might recall that when the Reynolds number is very small, we can effectively neglect the density because the inertial forces can be ignored. This means drag is purely due to viscous forces. If we neglect density, we have the following major variables to consider: our drag force, which here we call F to be general, viscosity, a length scale L, and velocity. Our goal is to get the drag force as a function of the other variables within a constant. So you set up the general equation where each variable gets an unknown exponent. Now, we only need to make sure that the base dimensions, mass, length, and time, on the left-hand side of the equation match the base dimensions on the right-hand side. Gather the base dimensions for each variable. Set up the base dimension equation with exponents. Gather all the like base dimensions and distribute the exponents accordingly. Now set up a system of equations for mass, length, and time independently. This lets us solve for the exponents. We get that the drag force d goes as the product of viscosity, length, and velocity to a constant. Not bad for not knowing any physics. Comparing to reality, for a sphere at low Reynolds number, the drag goes as 6 pi mu r u, where 6 pi is our constant, and r for us is the same as our length scale, L. In reality, I think the circled equation is more useful because for robotic applications, you could just run a few tests and tune that constant directly to your problem, instead of relying on the sphere estimation. Let's do the same thing for high Reynolds numbers. When the Reynolds number is much larger than 1, we can neglect the viscosity, mu. Here, we're going to go through our dimensional analysis again, but in double time. Gather your variables, F, rho, u, and L. Set up your generalized equation that you want, F as a function of rho, u, and L. Set up the base dimension equation. Gather like dimensions and distribute your exponents, and solve this system of equations for your exponents. In the end, we get that the drag force d goes as density times velocity squared times length squared. In reality, this d equals cd times 1/2 rho u squared a, where c sub d is a constant that depends on the shape, which is called the drag coefficient, and a is an area that is equivalent to our length scale squared. Again, dimensional analysis gets us sufficiently close to the right answer, within a tunable constant. These two equations are quite common in fluid and aerodynamics. The first low Reynolds number case is called Stokes flow, where drag goes linearly with length and velocity. The high Reynolds number case is the aerodynamic drag equation, where drag goes as velocity and length exponentially. As you can see, Knowing your flow regime and choosing the right drag equation is critical to knowing how much thrust you need to produce. And this brings us to the thrust force, how we propel ourselves through a fluid medium and generate enough thrust to counter drag. There are many different ways to produce thrust, and we can't go into detail on all of them, but we can review a bunch. Recall the way that a fluid feels force. The fluid acceleration is due to pressure, viscous, and body forces. We can make use of these forces when we want to propel ourselves through a fluid, so we'll categorize the thrust strategies based upon the force sources. The ways to produce thrust force are drag-based thrust. Like a canoe paddle, you move some object through the fluid and a resistance force is created. If the resistance force is in your direction of motion, you have a thrust. There's also lift-based thrust. This is based off of the aerodynamic concept that curved aerodynamic shapes can change the direction of the flow, thus producing lift. If the lift is in the direction of motion, it's also a thrust. Fish and swimming mammals like tuna and dolphins make use of this type of thrust in water. These are the two thrust sources based off of pressure force. The next thrust force type is added mass thrust. If you accelerate a body in a fluid, it will also accelerate a region of fluid nearby. This accelerated fluid has a mass and an acceleration, so it produces a force. And this force can be utilized as thrust. Additionally, you can also get thrust from direct momentum injection. If you eject a jet of some fluid into another, you have a mass flow rate out of your nozzle. This mass flow rate and the jet velocity make a force and is a common thrust force for things like torpedoes and even jellyfish. These two thrusts, the added mass and direct momentum injection, are associated with direct fluid acceleration. Note here the pressure thrust forces are for high Reynolds number concepts and are reserved for big, fast-moving vehicles. For very slow and small vehicles, we have the viscous-based thrust force. Here, we have something like bacteria with little mobile arms that stick out. Because we're in the low Reynolds number limit, we cannot produce thrust from symmetric motions. In order to get thrust out of viscosity, you need non-reciprocating motion. In this example, the arm has one shape on the upstroke and a different shape on the backstroke, producing a net thrust. Similarly, some microorganisms use helical spinning of their tails, which primarily pushes a fluid downstream to generate thrust. These are popular thrust forces for tiny robots and are subject of a lot of cool research right now. So keep in mind that at these very low Reynolds number limits, where flow is completely reversible, motions have to be asymmetric. For more info on this type of thrust, the Wikipedia article for scallop theorem is a good place to start. Lastly, you could always generate thrust via the body force. If your robot is magnetic and you pull it with a magnet, it will move. The options here are pretty broad. Note that often body forces are used to generate motions for viscous-based thrust, like causing tiny robots to oscillate or spin with electromagnetic fields. This is because the robots are so small, it's very difficult to design the thrust mechanism that produces its own motion. These types of thrust, viscous and body force thrust, are both fairly reserved to small, slow robots. And that concludes the thrust force types. There are likely more, but I think these are the major players that cover a wide range of applications. In practice, you will generally do the following. You'll define your objective. What do you want your robot to actually do? What are its tasks and motions going to be like? Then you have to assess the fluid. Is the fluid even important? Is it non-Newtonian? What is the density and viscosity? Then, determine your flow regime, likely with the Reynolds number. Big, fast things get different equations than small, slow things do. Next, you'll want to run some tests and fine-tune your control algorithms. how do you find those constants in the equations we derived? And finally, you need to design a thruster to overcome the drag. At small scales, this can actually be quite challenging. You likely need to iterate between the testing stages and thrust stages before coming to a final design. And that's it. Let's review. We started by going over all the meaningful differences between liquids and gases and how it impacts vehicle motion. Then we explored the equations of motion for a fluid, which is a complicated version of F equals ma. In general, the fluid acceleration is due to pressure, viscous, and body forces. The Reynolds number tells us what type of flow regime we're in. Big, fast vehicles can neglect viscosity, while small, slow vehicles can neglect flow inertia or density. To move, we need to overcome the fluid drag force with a thrust. Drag forces are different for high and low Reynolds numbers. Low Reynolds numbers get Stokes' law, where drag goes linearly with velocity and length. High Reynolds numbers get the drag equation, where drag goes exponentially with velocity and length. The types of thrust forces were categorized based on their force type. Pressure forces included drag-based and lift-based propulsion. Added mass and momentum injection are types of fluid acceleration. And viscous-based thrust is used in small-scale applications that require non-reciprocating motion. Lastly, body forces are a limited way to move a robot through a fluid. In practice, you need to define objectives, assess your fluid, determine your flow regime, run some tests, and refine your thrust design. Then you can iterate until you're satisfied. I hope you enjoyed the video, and thanks for watching.